Alright, so today we'll discuss in more detail the mechanism for a unimolecular reaction. So as we know that for a bimolecular reaction or the elementary reactions can be actually either bimolecular, elementary reaction can be either bimolecular or it can be unimolecular. So in bimolecular reaction, what happens is that there are two reactants that gives you the product, and in a unimolecular case, a single reactant gives product. So the probability of three-body collision is less, and that's why we say that there is no such thermolecular reaction, but there are certain examples, very few examples, where actually you can have three-body collisions. But we'll restrict our discussion on bimolecular and unimolecular reaction. When the reaction is happening, it's pretty obvious that there are basically collisions between reactants. Okay, that will be the products. Now we can do it in two ways. One is that we can actually solve the equations of motion and do the dynamics, but that's a more rigorous way, because if you think that we have to basically solve either the classical Newtonian equations of motion or the quantum mechanically, the Schrödinger equation of motion, Schrödinger's equation. So then the problem will be in a macroscopic system you have huge number of atoms and molecules, so which you cannot solve. So an alternative route is basically looking at the problem from a statistical point of view, and that was the essence of transition state theory, which we discussed already, but we will discuss in a more rigorous way now. Now this requires some knowledge of classical statistical mechanics, which we will skip, but we will give a handout, which you can follow and see how basically you can actually connect it to the classical partition functions. Now, before we go to the unimolecular reaction, we'll first discuss the bimolecular reaction, as I said. So, for a bimolecular reaction, if you remember that there are two molecules, okay, which are basically colliding with each other, and then the question was that what Eyring and Polanyi visualized is that there is a potential energy surface. This is basically the potential between the molecules, which is the reactant species, and then basically this side is the reactant side and this side is the product side. So reactant means here I have A plus B, and the idea is that if this overall energy, which is basically, you can see the energy which is along the line of center of the two species, if that actually exists around certain amount, let me call it as say E0, which is the threshold energy, then I'll get a product. And then they said that everything happens, basically the dynamics you can actually think of going through something like a transition state, which actually exists in between the reactants and the products on the potential energy surface, which means actually this reaction A plus B going to product can be thought of as going through a transition state. And then if you remember that Eyring and Polanyi, they said that we can actually think of a equilibrium. It's more correct to call it as a quasi-equilibrium between the activated complex and the reactants, and then the activated complex is basically forming the product with some rate constant. And the challenge was basically to model this system, and then they said that okay fine, since there is an equilibrium, they said that always you can write an equilibrium constant in terms of the partition functions, and then they use the statistical mechanics. But the entire point here is that when they formalized this theory, which is known as transition state theory, in the sense that there is a transition state which we are denoting by this notation dagger that exists between the reactants and the products, but the version which Eyring and Polanyi gave is more correctly known as activated complex theory, in the sense that they kind of visualize that there is an activated complex that exists in between, which I am denoting as A dagger. And if I know the statistical mechanical properties of this activated complex, I can calculate the rates. So it is more widely known as activated complex theory, which we discussed, or which is also discussed in any elementary text or physical chemistry. But later, people realized that this version, which was given by Henry Irving and Evans, and as well as Michael Polanyi. So I'm just writing Irving and Polanyi. Later on, people kind of realized that, look, this activated complex is actually situated on a particular point on potential energy surface, in the sense that its coordinate is fixed, and the way we derive it, that things are moving from left to right, which means actually its momentum is also fixed because I have a fixed energy. So if you have a fixed position and fixed momentum, which means actually it is inherently a classical mechanical theory. Okay, any transition state theory is actually classical mechanical theory, but when Irving and Polanyi was computing the rate constant using the partition functions, they actually used the quantum mechanical partition functions using Schrodinger equation, and basically for translation and partition function they used particle in a box model and so on. Now the question was, this was actually, this is a very very subtle point, and then the physicist Wigner, who is very well known for his work on neutrinos and many other theoretical physics, he said, he pointed out around the same time that it should be a classical theory. But that time it was not very popular. People realized it much later that what was Wigner point, and that's what we are going to discuss today. Wigner said actually this is a dynamical theory, in the sense that although we are doing statistical mechanics, like dynamics is kind of inherent here, and I can actually solve classical equation of motion, okay, to show that ultimately it will reduce to the same activated complex theory. Now, just to begin with, this activated complex theory already they showed basically you consider an equilibrium and there will be a delta G for the equilibrium, because in equilibrium constant you can write it as e to the power minus delta G by kBT, and that delta G you now connect it to partition functions, and from there if you just do an analysis, and also this K2 is basically, once the activated complex is formed, it is basically the rate at which the activated complex is giving you product. And Irving and Polanyi thought that it will be like this molecule will have 3n minus 6 or 3n minus 5 degrees of freedom, one of the vibrational degrees of freedom, which is very weak and which is along the reaction coordinate, that will give you the product. And then they basically came up with a relation, which is a very celebrated equation. So they said that the rate constant of the bimolecular reaction, you can show that it is basically a combination of constants. Kb is the Boltzmann constant, is the temperature, absolute temperature, H is the Planck constant, and then it is nothing but the partition function for the transition state. You can actually write it as QAB dagger divided by the partition function of the reactants. But this QA dagger is slightly different. I will use a prime notation in the sense that it is not all the partition function. 1 degree of freedom is actually taken out, and that's what they shown, and that's what every textbook also shows. Now they said that there is no such dynamics. It is just thermodynamics, in the sense that there is an equilibrium, okay, and all the equilibrium I'm casting to actually partition function. Now let us say what Wigner said, or how the Wigner basically visualized the problem. Now this is a bimolecular reaction, although I have shown it as a one-dimensional potential energy curve. In reality, it will be a multi-dimensional potential energy surface. And what Wigner said is that, okay, fine, let us visualize that I have two regions. Similarly, I have a reactant region, I have a product region. I can use the same figure. And then there is some kind of surface which is lying at this region which is close to the transition state region. This is called as something like a critical surface. So the critical surface basically tells you that if trajectories come from left, okay, and if there is no recrossing in the sense you can think that there is a surface and there can be reactive trajectories which actually come back, then actually it comes to the product reactant side. But if I assume that there is no recrossing, okay, then all these trajectories which are passing through this surface will give me product. Now, in the dynamical theories of using quantum dynamics, using something known as reactive flux, we actually compute these trajectories, okay, by solving Schrodinger equation of motion. But that's a very tedious job because you cannot solve it for you have to basically do a sampling, okay, over many initial conditions of the reactants, and that's a tedious job. Now, what we will show is that, okay, fine, let us think that, okay, fine, I have a transition state here, and all I need to know, okay, is how many trajectories are basically what is the fraction of molecules, okay, which are crossing this surface, okay. Now, he had in his mind, back of his mind, very much dynamical picture in the sense that there are trajectories, but how can I actually avoid computing the trajectories? That is the inherent picture. Now let us try to understand. Now here the picture what I have drawn is basically this axis is a coordinate, right? It's basically the positional coordinate, and this axis is the energy. But you can actually cast everything to phase space in the sense that I can actually think that for example, for a one-dimensional system, right, I can actually have different position. I can write the position as Q at different times. This will actually describe the dynamics of the system. Alternatively, I could use the position and the velocity, okay, which is basically the Lagrangian formalism, or I could use the position and momentum, which is the Hamiltonian formalism. And so basically, what I'm trying to say here is that I can actually, instead of writing it as a Q versus T curve, I could have actually cast the problem as a PQ, PQ notation, in the sense that I can cast the entire thing in phase space. Okay. Now, we just said, let us think that there is a phase space, okay, and there is a phase space volume, and I have a surface. All I need to calculate what is the fraction of the molecules which are lying here. So that I can calculate by calculating the phase space volume. How? Now, basically here we are calculating the number of states, right? Or basically the number of molecules. You can show, suppose I have a phase space area, something like that. What I am saying here is that this area is allowed for that critical surface. Now, how will you calculate the number of states which are lying here? The fundamental assumption here is that the minimum area in the phase space, this combination P times Q, which has a dimension of action, okay, will be something like equivalent to the Planck constant. Now here we are kind of using the notion of quantum mechanics, but in an ad hoc way. This is the only quantum part here, okay. In the sense like you will now say that, okay, fine, I'll just divide this phase space area. Each of them has basically area H. And then what will be the total area? Total area will be fine. So I have, say, dp dq will be the differential area. I'll integrate over this thing, okay. And if I divide by unit area, then I should get the number. How many number of squares are lying here? As simple as that, okay. Now this is not actually, this is for a one-dimensional problem. For one dimension, you will have basically PQ1 phase space, right? But then, as you can see, that if I actually extend it for a system which has n atoms, then I'll have 3n positions and 3n momentums also, right? So basically, it will be a 6n dimensional problem. Clear? Okay. So we'll not try to draw it, but the idea is very simple that okay, fine, I have some differential area here. First I will calculate that area and then I will calculate the entire area. In the sense that I will calculate the area and divide it by the correct dimensionality to calculate the number of cells, which basically tells you the number of states, which again is basically the fraction of molecules which are there. Okay. Alright, so let us try to calculate it. So what we are saying is that I have a surface, I have to calculate the entire surface, which is the critical surface. Okay. But let us first consider a small subsurface there. Okay, and I am asking the question, what are the number of states there? Okay. So this number of states I can easily calculate. So this is basically, I will have for any phase volume. Okay, again I'm just writing it in a more mathematical way. So this is suppose a volume of phase. Now how do you calculate the volume? I said that like there are 3n coordinates and then there are 3n conjugate momentums. So the coordinates I'm writing at dq1 to dq3n, okay, and then there will be 3n conjugate momentum, okay. Then I have to integrate this, okay, and there will be basically 6n integrations. So that will give me the total volume. And with this total volume, now if I divide by the volume of each unit cell, then I should get basically the number of states for that given volume. Now for one dimensional, if you remember, each PQ combination was giving me a dimension which is H, which is an area, right? Here, each PQ combination will give me H. So 3n PQ combination will give me actually H to the power 3n. Okay. So if I divide this thing by H to the power 3n, okay, that will give me the total number of states. Okay. Now what I am going to do is that I will first try to calculate what is the fraction, okay, of molecules which are basically here, and then I will integrate over on the critical surface. Okay. And I am assume that this fraction will be of course connected to the reaction rate. Now let us first try to calculate this fraction, this differential fraction. So what I am trying to say here is that here I am using a notation which is star. Now star means, if I try to draw it again, that I had a surface, okay, and any state on the surface I will just denote by dagger, okay. Within the surface there is a subsurface which right now I am just denoting as star, okay, and then there is a global phase space area where actually the reactants and products and everything is there. Okay, so there is a reactant region, there is a product region, and then this surface is dividing, and this surface is basically the transition state surface. Okay, now let us first calculate what is this probability, dn star by n. Okay, so according to classical the number of states, which the way we basically wrote it, if you remember that if I write this fraction, okay, so by using statistical mechanics, again it's a classical statistical mechanics, okay, so that we can actually give you a handout. That basically says that I should take the Boltzmann factor and then so what I did here is this fraction, okay, this differential fraction, what I'm saying here, will be dependent on a Boltzmann fraction. That actually comes from classical statistical method, but you have also seen it, like in partition function, I have always a e to the power minus E0 by kBt, but at this point, this h is a classical value, just classical. And this, of course, in order to calculate the number of states, I definitely have h to the power 3n, something like that. Okay. Divided by n. Now, what is n? N is basically the total number of states. Okay. So n is nothing but something like an integration which is exactly like that, 1 over h to the power 3n, okay, which has 6n integration. Now look at the notation here. So what I did here is that I am using the dagger notation here, just to clarify that this part is actually for n star, which is basically lying here. Okay, but I actually don't need n star. I have to go to n star to dagger, so which means I have to also integrate later on. Okay, so this is a small part of the critical surface. Okay, at this point, and then of course this h to the power 3n and h to the power 3n will cancel. Okay. Now, what is this n? This n is nothing but the total probability of the states, which are basically the starting point. The starting point, if you remember, that this n is nothing but the total number of reactant pairs. Okay. And this dn star is basically the differential number of, okay, basically differential number of reactant pairs that lie in the critical surface. Okay. Basically this ratio. Here. Now this is the meaning of the ratio. Now how do you calculate the total number of reactant pairs? Now suppose if I have 10 molecules of A and 10 molecules of B. If I calculate the pair, it will be just 10 into 10. Because each one will have A will have 10 B's, something like that. Okay. So this n is nothing but total number of A times total number of B. As simple as that. Clear? Okay. Alright. Now let us consider this part. Okay. Now this is nothing but the I missed I to the power minus h here. Now according to classical mechanics, okay, so this is nothing but the partition function, right? Partition function of what? This is a partition function of everything. So basically this is the partition function for the reactants, okay, QA or QB. But if you remember, when we do this thing, like we take the total partition function is basically the multiplication of translational, rotational and vibrational and electronic. Now translational, we always do get a V, because if you remember that is you will get a L for one dimension and then you will get a L cube or V for 3 dimensional. So this Q which we will get is the translational partition function times volume, because the volume will the total partition function times volume. So basically I can write it as this, the denominator. This is nothing but partition function of A times the volume. Volume of what? Volume of the content. Yeah. Which one? No, so what I'm saying here, I have the total Q, right? So the total Q is Q translational, okay? Now, the expression for the Q is this. If I divide it by V, then I'll get rid of this thing. Okay, but the V will always come because whenever you, like if you start from a particle in a box, so you get something like 2 pi n kT to the power half, right? And then there will be a L, right? If I extend it to 3D, so it will be 3 by 2 for a particle in a cubic box, then HQ, and then I have LQ, so the V will always be there. So this we write as Q trans, okay, and this is the V, okay. So we should always say that transitional partition function are uniform. So here I am just including the volume and come back to it, and this is nothing but UV into V, right? And numerator is the same. We are not changing anything. Now the question is, okay, fine. What I have to do is that this is at this point. This is basically what I calculated. Is what is the fraction of molecules, okay, that are lying in the small region of the critical surface, okay. And then I am asking the second question: what is the rate at which they are crossing the surface? Okay, that will be basically the number of molecules which are there, okay, and the speed at which they are crossing. Meaning, all I am now asking is that I know the rate will be somehow related to this quantity dn star dt, how they are crossing. But of course, dn star only describes a part of the thing. So I have to eventually integrate it over the phase space for the critical surface, not the entire thing. Okay. So we will do step by step. Now first do this thing, which is dn star dt. So what is dn star dt? Now then we can basically say that, okay, fine, it's a very high dimensional thing, right? And it has basically many positions, many momentum. Now only 1 degree of freedom, okay, is basically the reactive degree of freedom. Let us say this Q1 dagger is the reactive degree of freedom. So whenever I am taking a time derivative will be applicable only to this, not any other. Like it's not a chain rule of differentiation, because all other are not changing, positions and momentum are fixed, okay. So I'll take a time derivative for only this movie. Clear? Okay. Secondly, let us try to understand what is this H. As I said, H is basically the total energy, right? Which is basically the kinetic energy plus potential energy and everything. Okay. Now this H I can write, okay, as some energy which is basically spent for that motion. Which motion? Which is basically the how the dq1 coordinate is taken. Okay. Now the picture is something like this. Like I have a surface, right, and I am considering a small surface right now, and only one coordinate is taken, which is q1 dagger. Why dagger? Because it is on a dagger space right now. Okay. Now anything related to a motion, I can actually consider classical like kinetic energy. Kinetic energy expression is p squared by twice m, right? But this is associated with only the p1 thing. Okay. So it is basically p1 dagger, that squared by twice n, but instead of n, I am just using some reduced mass. Okay. Plus the rest of the thing. The rest of the thing basically describes Q2 to Q3N and all these things associated. Okay. So the energy I am just partitioning. I am saying that due to this crossing, which is basically the reactive crossing, I have some energy, and that is needed. Clear? Okay. Now let us come back here. Okay. So what I have e to the power minus h by kVt, but that h I already told that it is partitioned. Partitioned how? that it is basically H prime plus H del, right? Yeah. Okay. And I'm just following from here to here. I had one n in the denominator. Okay. That n I can bring it here. Okay. Eventually what I'll do is that I'll just have n is nothing but n and n. Okay. So this n, there is a 1 over n. Right? I'm taking the time derivative of the entire thing. Okay. So the next step what I'm doing is that ddt of this entire thing. Okay. So that will give me 1 n that I'm just taking there. Okay, and already I said that it is reactant pairs, Na times Nb, and I had actually two V's in the denominator. Okay, so I can just divide it by V, this divided by V. So in the denominator I have only Q and Q, which are partition functions per unit volume. Here, now let us look at the numerator. Okay, I have what? H to the power 3n e to the power minus h by kBt, and then there will be a time derivative which is acting only here. Okay, so what I am doing is very cleverly is something like this: is I have e to the power minus h prime, that is nothing but p1 dagger square by twice mu, right? Okay, and then I have this guy. Let me first write the constant h to the power 3n. Okay, then I have this guy, but that I will write it as dq1 dagger dt, because that is the only thing that is changing. Okay, rest is the same. Now what was my rest? The rest was e to the power minus, I already have taken care of h prime, so I am left with h dagger by kBt, right? And what are left? I have dq2 to dq3n, right? And I have dp1 to dp3n. These are all dagger. Clear? Because dq1 already I have taken here. Clear? Okay. Now the next thing is, okay, as I said that this is basically red, which describes the red due to this region, but I have to basically integrate over the entire region. Okay, basically I have to integrate then this thing. Okay, which will be the red by definition, because the red by definition is what are the probabilities or the fraction of the molecules, okay, that are lying here. But remember that fraction of the molecules lying in the critical surface automatically means that this is basically the probability of the molecules those have the energy which is crossing the barrier. Okay. Second thing is that I am calculating rate, so it is not the number but at what per unit time how they are changing. That's why I have to take time derivative. Okay. So the rate of the reaction, okay, should be nothing but this quantity which I uploaded. Okay. But then I have to integrate it over all the spaces. Okay. Because I have to now say this is the condition and then I am calculating. Okay. Now, here's the thing. Let me integrate it. But before we integrate it, let us see here what I am doing. So, look at it. What is Na by V? This is basically density of A. Similarly, Nb by V is density of B, right? So, what I'll have is 1 over Qa Qb, that thing will be there. And eventually, I'll have A into B. Just a bimolecular solution. Okay. So, what is the numerator? Now, look at it very carefully. I will integrate this equation. Okay. But I will integrate it very cleverly. In the sense, I have h to the power 3n. Okay. That I will split as h and 3n minus 1. Okay. So let me just write this thing h, okay, and then I'll do a single integration for the q1 coordinate. Okay, I have just a problem. I can actually bring this p1 here and I'll just integrate. That's the thing. But look at it. I have dq1 dagger dt. Now what is p1? P1 is momentum, right? Now p1 dagger means actually mass times velocity. Now velocity is what? dq dt. These are all dagger. Okay. So this guy, dq dagger dt, is nothing but p1 dagger divided by v. Okay. So I'll just write it that I have e to the power minus p1 dagger square by twice mu. Okay. Just follow it carefully. I have one extra mu, reduced mass, that I am just putting outside the integral. It's just a constant. Then I am left with p1 dagger. Okay, because it was p1 dagger by mu. And then there is a dp1 dagger. Okay. Clear? This is just one integration. But there will be 3 n integrations. Actually, there are 6 n integrations basically. Okay. So all others, I'll just write it together. Meaning, I'll have 1 by h to the power 3n minus 1. Okay. All these things, which is starting from dq2 to dq3n, dp2 to dp3n, with e to the power minus h dagger by 20. So basically I partitioned the energy. Okay, one energy was associated with the kinetic energy and the other energies are, I don't care. Okay, which are associated with the positions and their conjugate momentums, excluding the particular coordinate. Okay. Now this itself, as you can see, is basically another partition function which has 1 degree less, because that degree I calculated separated. And how I did the separation? This is the separation. Clear? Okay. And here I have A into B. Clear? Okay. Right. Now just I have to solve this integral. Okay. Now again, so what is the range of the integration? So I am adding momentum here. The momentum should have all possible range, 0 to infinity. Okay. So this is necessarily a gamma function integral. Okay. And the gamma function integral, if you remember, it is something like e to the power minus x to the power n minus 1 dx. That will be basically gamma n by a to the power n. Okay. Now how will you connect it? Okay. Just look at it. So here I have something like e to the power ax square. This integration is something like e to the power minus ax square. Okay. Dx. Something like that. This is the integration, right? 0 to infinity. Because I see that there is a p square term and the variable is p. Okay. Now there was an x also. Something like that. Okay. So what is the trick? The trick is that first you look at here. It is x square. Okay. So what I'll do is that I'll not touch this one. Okay. I'll just make it as e to the power x square. But this guy somehow I have to make it as x square. Okay. Now I can actually write it as d of x square. Okay. Now if I write it as a d of x square, I'll have 2x dx. Right? So I have to use something like half factor here. Okay, the x already I included here. Okay, but then what I have is x to the power 0. Okay, or basically I have x square to the power 0. Okay, 0 is basically 1 minus 1. Okay, now that is the integration. Now you can again make a change in variable that x square is now z. Okay, and if x square is z, the limits will be same, 0 to infinity. So it is now e to the power minus az, z to the power 1 minus 1 dz. Okay, that is gamma n by a to the power n. Gamma n is what? Gamma n is gamma 1. Okay, by a to the power n, a is basically also that whatever the constant. So this will be nothing but 1 by 2a. Okay. What was our a? A is basically this thing, 1 over 2. Okay. So this will be nothing but 1 over 2 into 2, right? So what I will have is mu. Okay. Now you see that this is just mu, and this mu will cancel. Okay. So what I will have is basically we did a mistake here. So we wrote the Hamiltonian, but we did not write the cavity. This will be p square by twice mu cavity. So the A here is twice mu cavity. This is basically mu cavity. Clear? Okay. So if I have mu cavity here, what I will have, this mu and this mu will cancel. Okay. So if these two cancel, let us just write the rate once again. Rate for bimolecular reaction. So the rate will be nothing but I'll have kBT by H, right? Because this entire term will give you kBT by H. Okay. And then all these things, but all these things are nothing but, as I said, this thing is giving me kBT by H. Okay, it was kBT mu. H is actually kBT mu, and this mu is cancelling. So I'll have kBT by H. Okay, and for this integration, I'm just writing it as it is also a partition function. Clear? Okay, but which has 1 degree less. Okay. Let me just write it. It is when I wrote the rate, I should write it not this one but per unit volume also, because this is just a number. Rate is defined as the concentration. Okay. So remember, this is basically partition function times volume, and that volume will cancel. Okay, so I'm not writing it in the final form. Okay, and then I'll have QA. This is exactly the same expression as ideal expression. Okay. Now, what is the essence? The essence here is that then we are short. This is entirely classical mechanics. Now, what is the trick? The trick is that I am thinking that I have in my phase space, okay, things are moving around. There are trajectories which are moving from reactant side to the product side. I am considering there is a dividing surface which I call as a critical surface. Okay. Now, I can calculate what are the number of trajectories which are going from left to right, per unit time, per unit volume, that is my rate. But instead of calculating that way, what I did is that I just calculated what is the probability or the fraction of molecules which are lying in that dividing surface and at what rate they are crossing. Okay, that's what we cleverly did. But as a result, what we see here is that inherently, number one, these dynamics can be shown as a classical dynamics. Okay, because these partition functions are all classical partition functions. Thus, H was just p square by twice mu, all classical. Okay, but I get the same expression. Secondly, it is inherently dynamical because I consider dynamics. This is actually 1 degree of freedom which is crossing. Okay, but finally I don't care because I am integrating out all the dynamics and I am getting the canonical partition function. without invoking any idea that there is equilibrium between the transition state and the reactant. I need that equilibrium because I have to connect it to the partition function, because there is a relationship between equilibrium constant and the partition function. But here I did not actually consider anything. I just said things are moving from left to right, which is very much dynamical, okay? And there I can also compute everything, okay? The partition function came only to calculate the number of states or the fraction of states. Now, the triumph of transition state theory is that versus the dynamical theories in the sense like where you actually do reaction dynamics, okay, is that here, now it is a state counting problem, like, meaning you can actually just use your electronic structure theory to calculate the partition function. You are not solving any time-dependent equation, be it Newtonian, be it Lagrangian, be it Schrodinger equation, okay. The time already is inherent, but it got cancelled, because kVt by h has a dimension of rate, okay. So then you can just do electronic structure theory, solve hi equal to hi, what are the density of states, and then you can calculate the partition function of A, partition function of B, partition function near the transition state, and if you can calculate the density of states, then you are done, okay. Then you don't need to do any dynamics as such. Only that hi equal to hi solution will give you the dynamics itself, because I have derived the equation. Okay. Now, from here, let us just see how to basically go to the unimolecular. Right. The unimolecular, we already discussed that there is a model which was like unimolecular reactions. Initially, people are thinking that it happens due to radiation. Now, if you don't have light which gives you the radiation, then they say that any reaction is happening in a container, and any container has a background radiation, thermal radiation, which is the blackbody radiation. But then there are a lot of controversy, and then people showed that radiation cannot do enough excitation, which can cause a breakage. Then actually Lindemann proposed that okay, so there should be a bimolecular reaction that precedes the unimolecular reaction, which is basically A2 product. But this M is a second body which can be an A, another A molecule, which can be the wall of the container. And due to this collision, we have an energized molecule. Okay, there can be a deactivation, collision and deactivation, and once in a while, this A star actually gives you a product. So the essence here is that there should be a bimolecular collision that precedes the unimolecular reaction. Okay. So I can have the rate constants like K1, K minus 1, and K2. And this is a very straightforward thing, like if I apply the either the equilibrium approximation or so if I just consider there is a first equilibrium, the overall rate you can always write as something like K1, K2 divided by A minus 1 into M plus K. Now this actually appears everywhere, this kind of model, like steady state approximation, model everywhere it appears. So you'll always get this kind of equation. Times, of course, okay. Now we can quickly see here, if I have a high pressure limit, because these initially were all done for the gas phase, what will happen for the high pressure? Okay. High pressure means actually the concentration of M is very high. Okay, so you can easily see that. Okay, so before going to that, we always write it as something like K unimolecular equilibrium. Okay. You can see in the high pressure limit what will be the K unimolecular. So I will have M here. Okay, so K1 minus 1 into M is much greater than K2. Okay, so I will have K1, K2 by K minus 1 and M is cancelled. Okay, so in the high pressure limit I will have K unimolecular, which will write it basically as K infinity. Okay, it's high pressure. That is nothing but K1, K2 by K minus 1. Okay. And similarly, I can also think about low pressure limit. Okay, so the low pressure limit is something like unimolecular, which we write it as K0. Now low pressure means this term will be small, so I'll have K1, K2 by K2. So K2 will cancel. So what I'll have is K1 into N. Okay. So these are basically the two limits of the unimolecular reactions, and Lindemann basically successfully found that at low pressure limit, if I just plot the rate constant versus the concentration of the species, as you can see that at a very low pressure regime, okay, as you can see, which one? Yeah, but I'm just writing the unimolecular thing. I wrote A separately. Okay. So yeah, so it is something into this thing, and I'm approximating that thing. So A I'm not writing. So now the question is, how do you calculate this individual rate constant? Okay, for unimolecular reaction. Now there has been many theories. Now the first successful theory was basically now you can think like what will be the rate of the unimolecular reaction. You can proceed with say bimolecular collision from your Maxwell-Boltzmann distribution, and then you calculate the collision theory. Okay. And then you can think that K1, okay, will be something like your collision frequency, right? But not all collision will give you a star. You can think that there will be some probability that I cross this energy, then only I can actually get this. Okay. But the deactivation part, okay, will be something like see, deactivation does not need any like it's a de-energization part, right? So basically I can write it as Z minus 1, but Z minus 1 and Z plus 1 are same, because forward or reverse, it is basically collision between A and M or A star versus M, but it doesn't care, it's a kinetic energy thing, right? So what is the total number of molecules, what is the temperature? But A star is actually going into the internal energy. So the deactivation of the activation doesn't matter. But for activation, I definitely need to cross the barrier. Okay, for deactivation, the assumption is that you don't need to cross any barrier. You can deactivate, just lose the energy. Okay. And if you take the ratio K1 by K2, K minus, sorry, this should be the K minus 1. Okay. So you'll get basically an Boltzmann factor. Okay. So the rate is nothing but K2 into the high pressure limit. Okay. So this K infinity is nothing but K2 into e to the power minus E0 by K, but which is not correct. And people when plotted it, okay, E0 you can get from RNA's parameters, okay. So, but then when they plotted it, they found that it doesn't match. Okay, and it's a huge deviation. Another question was why huge? Then the first thing, what? So this is the Lindemann hypothesis, and then the next thing came, and next like significant modification was made by the American physicist, chemist, physical chemist, Cyril Hinchelu. Okay, and Hinchelu said, okay, fine. What we said here is a kinetic energy. Okay, but in reality, what is happening? A star, a molecule having high kinetic energy, it is not the sufficient condition. It should have enough internal degrees of freedom. What are the internal degrees of freedom? Vibration and rotation. He considered only vibrations. Okay. And as a model of the molecule, he said that there are some 3n minus 6 or 3n minus 5 vibrational degrees of freedom. Those vibrations, he said, let us assume it to be harmonic oscillators. Okay. So I have basically S, small s, okay, harmonic oscillators, which are my system. So there are some S uncoupled harmonic oscillator, okay. And why uncoupled? Because I am just considering this to be very independent. Okay. Now this part will give an handout. Okay, where how to calculate this total, like how to calculate the probability. for this S uncoupled harmonic oscillator. Okay. Alright. So what he said is that fine. I'll just write this probability thing again. If I just calculate the fraction, okay, this, what is this fraction? This fraction is the differential fraction of the molecules, okay, of the probability that the molecules are getting energized, okay, and that, according to him, is basically I have suppose E0 amount of energy, okay, and what I'm doing is that there is some reactant and product, okay. So all these will say that suppose there is ester here. Okay, after the collision, and I have A here. Okay, and this much energy, suppose I am giving to the molecule. He asked this question: how this energy is distributed among this S uncoupled harmonic oscillator? That will be the most important thing to calculate. Okay, how the internal degrees of freedom are getting this E0? Because if it goes to the transition, it doesn't matter. The molecule will just fly off. Until it goes to the internal degrees of freedom, then only the bond breaking or making happens. Okay, that is the very simple thing. But this calculation we can show it later. Okay. So it will give you something like 1 minus s1 factorial, and then E by kt in your s minus 1. And then I'll have minus E by kt. So the book by Stenfield or Hendrickson Hansen, okay. So that has a little discussion how to calculate the density of state for an S harmonic oscillator, which are uncoupled. Okay. Because usually you do not solve the harmonic oscillator problem in the phase space and calculate it. Okay. So again, the total probability will be something like this. Okay. Now here's the catch. The catch here, Institute said that okay, fine. Look, this is what we have computed. We have computed basically what is the fraction, okay, of the molecules, how the energy is basically partitioned among the S harmonic degrees of freedom. That's it. Okay. But the necessary condition is that the reaction will happen, okay, if and only if. Okay, so basically I am trying to calculate this quantity K1 by K minus 1. Okay, I just cannot calculate over all the energies. Why? Because I need a minimum energy for the reaction to happen. Otherwise the reaction will not happen. Okay. So then the integration will be something like this. Now you can actually make a substitution like you can show it how to do it. So basically you write this thing. So this is the total energy, okay. And then all I am saying is that I need a minimum energy E0. Then the energy available for these harmonic oscillators is nothing but E minus E0, where E is basically fixed. Okay, and then we can make a substitution. Okay, and then we can actually solve this integral. I'm not solving it right now. And if you solve it, then you can show that this will give you something like 1 by s minus 1 factorial E0 by kt raised to the power s minus 1, and then I have e to the power minus E0 by kt. Yeah. Now, what we have done here, what Hinchel did, okay, is basically calculating this ratio, energization divided by de-energization. But then, that we do not do experimentally, or that we do not measure experimentally, right? What we measure experimentally is something like, say, the high pressure constant, okay, which is nothing but K2 times this thing. Okay. Now the question was, you can calculate it for any molecule, unimolecular reaction. I know what is gas. I can actually do a normal mode analysis. I can get all the frequencies. Okay, I know what is the number of is. I can calculate the threshold energy from experiment, and then I can calculate this factor. Okay, it's not very difficult to calculate. And then K2 is basically nothing but frequency of that vibration, which is the OPS vibration. That will give me reaction. If that one you calculate, okay, then again there was a problem. The problem was basically they found that it deviates from the experimental value by whole lot. Okay, and then another group of basically concept came that were focusing how to calculate K. Which means what Hinshelwood did a beautiful thing. Hinshelwood did the first step, how the energization happens, which was correct. But once I have the ester, okay, how that ester is giving me reaction, for that the other theories came. Okay. Now there are a systematic development for this thing, which is known as the RRKM theory. So the RRKM is basically comes from Ramsperger. Okay, so this is actually Oscar Rice. Oscar Rice and his postdoc Ramsperger actually gave a model which was also given at the same time by Castle. Okay, this is known as RRK theory. And later on, Rudy Marcus, as a postdoc of Oscar Rice, revisited the problem. Okay. And that's why it is known as RRKM theory. Okay. Now we'll skip the systematic development. It's very interesting though. Okay. But we'll directly go to the RRKM model. Okay. What is basically the essence of the RRKM model? Okay. So what is the essence? I mean, what basically Rudy Marcus said. Okay. Now, when Rudy Marcus was solving this problem, okay, in 1940s most likely, that time already transition state theory was known. Okay, Wigner's version was known. So he had in his mind very much something like a concept of the transition state theory. Okay. And then he said, okay, fine, what is happening here? Let us think about it. Right, I have again think about the energy. Okay. So suppose my total energy is fixed. Okay. Now what I am solving right now is that I have some threshold energy, same one like Hinshelwood was thinking. Okay. And this is the energy which is available to the molecule. Now this threshold energy again is kind of for crossing the barrier. Okay. And this energy actually I can write it as E dagger. It is something like a transition state notation. Okay. So E dagger will be nothing but E minus E0. Okay. Now what is said is that fine, all I have to do in the transition state spirit is that I can actually define density of state or number of states. Okay. So what is the meaning of density of state? Suppose I have some states here. Okay. Now I can actually calculate what is the number of states between say E to E plus D. Clear? Okay. So that thing will be basically the number of states at E plus D minus number of states at E. Now what will be the density of state? Density means it's the energy density per unit energy interval. So if I just write it like this, okay, that I call it as a density of state. Now, in the limit that this dE is very small, okay, then I can use a differential notation. Okay, which means then I can actually write it, this is nothing but dg, okay, and d. When actually these E's are very small, meaning this thing is kind of continuous. Because until and unless it is continuous, I cannot use a differentiation because it's a for continuous variable. Okay. All the molecular energy levels are discrete. We are kind of saying that for a particularly for a high energy process where actually you are crossing the barrier. Okay. So your density of states of course increases. Okay, so it's not a very bad assumption to begin with that there will be a density of state concept where actually I have a continuous energy distribution. Okay, so then this is the density of state expression. Now again, I can actually calculate this number G, the number of states for harmonic oscillator. That will show how to calculate. Okay, so that if we do it, so G basically is the number of states at energy E. Clear? Okay. So for S uncoupled harmonic oscillator, we can show that this number of states will be something like this. So this is actually small s. Even if I don't write, usually it's very small s. Okay. But mu i's are the vibrational degrees, vibrational frequencies. I have S harmonic oscillator, so I'll have mu1, mu2, mu3, all these things. Okay. So this is how you calculate. Now, how do you calculate it? So it is some give you the handout where we'll see this. For example, for a ellipse. Okay. So what is the equation of motion for an ellipse or a harmonic oscillator? Now I know the Hamiltonian is what? E square by twice mu plus half k square. Right? Clear? If the energy is fixed, suppose I am fixing the total energy. So then actually I can write this equation as something like p square by some constant square, okay, plus x square divided by some constant square is equal to 1. So that is the equation of an ellipse. Okay, but this is basically semi-major and semi-minor axis of the ellipse, right? So in the phase space, the harmonic oscillator thing will look like this for a fixed energy. If I increase the energy, it will have another contour something like this. So all we are doing is basically calculating this and then dividing by, if I divide by h, then I will get the number of states. As simple as that. Okay. But now this has to be extended to S harmonic degrees of freedom, not only just one. Got it? So the number of states you can easily calculate. Okay, so I have basically this thing, then you can easily calculate the phase space volume. Okay, because you know A and you know B, and the area of the ellipse is nothing but pi AB. Okay, so clear? This is S square and this square. So if I write this equation like this will be the area, and this divided by h will give me the number of states for a one-dimensional ellipse. Similarly, you can actually do it for like S dimensional ellipse. So actually there are S different oscillators. Okay, that will give you this thing. Clear? It will be called S divided by all this thing. Okay. Alright. Now this is the number of states. So what will be the density of state? Density of state is just you have to take the derivative. Okay. With respect to what? With respect to energy. Right? So what I will have is, you see here it is S, so I'll have S minus 1. Okay. So I'm just writing it first. I will have S minus 1 and then I'll have e to the power s minus 1 divided by I'll have I h mu I. This is going from 1 to okay. Now this is one thing. So if you remember that the rate constant which we did in the bimolecular reaction. So if you remember that the rate constant was something like, if you remember correctly, that that time we were considering that we have some number of states, right, divided by the total number of states, because that's how we calculated it. dn by dn star by n, something like that. Okay. So in the RRK model, actually you do it. Okay. And once you do it, you can show that okay, find this rate constant. Okay. Will be nothing but I have to calculate what is the number of states. Okay. Which are lying above E0. Okay. Divided by this quantity. Now, what is n? N is basically the density of state for the entire thing. Okay. Now, let me just write it here. So just now I have the expression for G as e to the power s is factorial and I have basically e to the power s minus 1 is minus 4 factorial or now think about it. What I have written, it is basically G dagger. It's the same concept. Okay, so I had a region in the phase space. Okay, I want to calculate the number. But when I calculate the number, there's a trick. The trick is that they say that 1 degree of freedom would be less, always, when you calculate. But when you calculate 1 degree of freedom less, meaning you have to isolate, you have to write this thing as something like for G dagger. Okay. You have to write it something like one combination which is 1E, okay, and 1H2 that you take out, okay, and then you write the rest of it, okay. So G dagger means actually the number of states which has one particular degree of freedom less. So this expression will be something like, it's a similar expression, as you can follow it. So I'll have something like E minus E0. Now instead of S, it will be S minus 1 point because there is one degree of freedom S. Okay. Here instead of S, I will have S minus 1 factorial. Okay. And here the summation will also be I equal to 1 to S minus 1. Okay. Divided by I have H and density of state. Okay. Divided by I have H. And then what I have, the density of state expression I already showed. It is e to the power s minus 1 divided by s minus 1 factorial times h u I equal to 1 to this. Now, again, think about it. This corresponds to this ratio. Okay, and this number of states corresponds to the entire region. Something like that. Okay. So now you can see there is a h here. Okay, this h and this h can be multiplied, and then I'll have the same dimensionality for h in the denominator and numerator. So I'll get rid of the h right away. Okay. So this expression is reduced to something like, it will be something like this over here, E minus E0 divided by E to the power S minus 1, right? And then I'll have an interesting thing here, I mu I, sorry, this should be my data, and divided by I mu I is going from 1 to S, I is going from 1 to S minus 1. What do you mean by this? Think about it. What I had is that I just like combine the e's, right? And then how the pi comes, but if you remember that when you write the harmonic oscillator partition functions, okay, all these h nu's get multiplied. Okay, so that is the notation for pi. Now what I am getting ultimately, look at it carefully, that I have a frequency. Which frequency? Which are the transition state frequency? Like the molecule when it is excited, that will have some frequency which is slightly different. These are actually new dagger. Okay. But then one frequency is less. That's why the sum is going from 1 to S minus 1. Denominator, I have the frequency which is the normal modes in the ground state. Like it's an overall thing. Okay, it's not the dagger region, it's the entire thing. Because that's why it gets basically the ratio and the probability. Okay. But at the end of the day, interesting thing to look at here is the denominator has one extra dimension. This will not just cancel because this set of frequencies are different from this set of frequencies. Okay. And also I see that the number is one less, which means overall I have a frequency inverse unit, which is rate. Okay. But this rate is not a thermal average rate. It is for a rate for a fixed energy. But you do not do the experiment at a fixed energy, you do an experiment with a fixed temperature. Okay. So this rate is known as actually microcanonical rate constant. Okay. So this is known as microcanonical rate constant. Okay. But from there we have to actually calculate K of T. Right? Now how do you calculate the K of T? You just have to calculate this K of E. Okay. What is it that if I have a fixed energy, which is E, given to the system, what will be the rate? Okay. Times I have to also calculate what is the probability of having the energy E for a given temperature, and then integrate over the entire thing. And then I will get the rate constant. Okay. That's what basically is the essence of the Marcus theorem. Okay. But how I arrived at it, I will skip it again. Okay. Because this needs a lot of mathematics. But essentially, as you can see, this will be still the ratio of the states. Okay. In some sense. Now. So what Marcus said is basically the similar thing. Like I have something, the energized molecule, okay, going to product, but then he said that it is something going to an activated complex. That is the essence of Marcus theory. Okay, the M modification of Marcus. The earlier expression which I showed is mainly due to the RRK version. Okay. Now, how do you get K of E? To basically get, I always can calculate K of E, okay, but then I have to say what is the probability that I have the energy E, okay, and then I have to integrate over all possible energies. That is the essence, okay. But then remember, this has not the lower limit as 0 because the condition is that you should have your minimum energy easy. Again, let me just draw the picture. Okay. This is what is happening. This is the total amount of energy fixed, right? And then I said I need minimum E0 to cross it, right? So the transition state basically gets a share which is E minus E0. Clear? Okay. What can be the total energy? If I reduce it, if I go up to E0, it will just happen, the reaction. If I go below, no reaction will happen. So I can have E like this. So this is for a fixed T. But now, for a fixed temperature, this E will also change. That's what I am saying. Okay. Now you will change in such a manner that it cannot be below 0. If it is 0, then this guy goes to 0. Okay. But E can go to infinity. Then this guy also can go to infinity. Okay. But the lower limit has to be 0. Okay. Now, from going from microcanonical to canonical means now I am saying that the E itself is right at a fixed temperature. But again, it cannot be less than 0. Because then this guy gets negative. That is meaningless. Okay. Now, what he said is that okay, fine. So I have basically in a cell token like the number of states. So okay, I can write it as something like the number of states, okay, which are having energy more than E0. Okay. This is exactly your transition state kind of expression. Okay. If you remember that we wrote it, right? Basically the partition function one, but right now actually we are following the density of basically this G dagger. Okay. And what was our K expression? Remember, we had G dagger divided by Hn, right? What was N? N is basically the total number of states, right? Now, if you remember, the density of states, basically. Okay. Now, that thing, you can always write it. Okay. Now, if you think that I'm just writing it like this, and what was the K expression? K expression was basically G dagger divided by Hn, right? But N is basically the density of states, okay, which you can connect, okay, to partition function. We are not showing it here. Okay, we're just saying that okay, fine. I'll have an expression something like this. Okay. Now this is the microcanonical part. Okay, and the probability is here. Just the Boltzmann probability. Okay. And all I have to do is to integrate between E0 and okay, keeping this picture in mind. Now I'm adding E also. Okay. Now the question is, okay, fine. Then let us think like how I will solve it. Okay. Now I have to do a changing variable. What is the changing variable? Look at it here. If E0 is fixed, okay, I can actually write, and E is also fixed for the microcanonical thing. Okay, but I can actually, instead of writing it as like E, I can actually make a changing variable as E dagger. Okay, so means this total energy E is basically E0 plus E dagger. E0 is a constant. So right now I can actually take out it out of the integral. Clear? Okay. So what I am saying here, I could write this expression as e to the power minus E0 by kT, okay, by HQ. Okay. Then this guy, think about it. E minus E0 is what? E dagger. Okay. So this is nothing but G dagger of E dagger. Okay. What is this guy? This is basically e to the power minus E dagger by kT. What is your D dagger? DE. DE is nothing but D dagger minus D plus D is 0, but D0 is a constant. Okay. So the changing variable only resulted in taking out a factor which is e to the power 0 by kT. Okay. But now, if the lower limit is 0, okay, what is the lower limit of E dagger? If the lower limit is E0 minus E0, it is 0. Upper limit E was infinity, infinity minus 0, that is infinity. So now I have actually 0 to infinity and a bit. Okay. Still, it is kind of what it is saying. It is basically saying I have a e to the power minus 0 by cavity, some h, some q. Okay. But look at it, I have basically something like G dagger, which is basically the number of states in the transition state area, okay, which has energy E dagger, and I am varying this E dagger. So think about it, if the total energy varies, this thing also varies because this is fixed. Okay, now I'm actually, this is my variable. Now this will also vary. So I've changed the variable from E to E dagger, that's it. Because E0 is a constant. Okay. Now this looks pretty odd, like pretty odd expression at this point, right? It is there is no like partition function and all these things. Now let us see how to basically cleverly compute it. Okay. Now look at it carefully. Now what is your this thing? Like I have, whenever we have this exponential thing, okay. Let me just write it like this. First, let me ask this question. What is this quantity? Okay. See, I have actually two variables. Okay. So I have to integrate by parts. Okay, because this is also a function of energy. Because density of states, of course, changes. Like number of states, of course, changes as a function of energy. Okay. Also, I have this Boltzmann factor as a function of E dagger. Okay. So I have to do integration by parts. Okay. But I'm just playing a trick. The trick is that, okay, fine, integration of parts, if you remember, like I have to do u integral vx and that way, right? And then there is a derivative part. So what is this one? If I do it, okay. So this will be minus, okay, 1 over kBT, right? And I have e to the power minus e dagger by kBT, d dagger, right? So this guy, okay, I could have written as this multiplied by minus kBT. Why I am doing it? Because see, now if I have this thing, I will have a kBT by h factor here, connecting to your like bimolecular transition state theory. But there is a minus sign. Don't forget about it. Okay? So there is a minus sign of kBT by h. Fine, I have taken care of the kBT by h term. Okay. I have also taken care of this e to the power minus 0 by kBT term, which also appears in the Artin equation. I also have 1 over q, which is gray. So that thing should be q dagger, basically. How? That's the question. Okay. So what I have now is integral 0 to infinity. Okay. This d dagger of e dagger. Okay. And e dagger, sorry, to d dagger of e to the power minus e dagger by k. Clear? Okay. And I should have written it like this. D of, yeah, it's a differential, isn't it? Clear up to this point, right? Now see, this is actually easier because I can actually use it as a first function. Because first function is basically integral of that, right? So if I just integrate, it will be the same thing. Okay. So let us just write it. So I have this factor, okay, minus kBT by h, okay, e to the power minus dA by kBT, 1 over q. Now let us look at it. Okay. So what I'm saying here is uv dx. Okay. So u integral of v dx. Okay. So u is basically this. Integral of this is the same thing. Okay. So time half is g dagger, which is a function of e dagger, e to the power minus e dagger by kBt, evaluated between the limits 0 and infinity, right? And then what I have is minus integral. Now what I have to take this derivative of this, right? And then the total integral. Okay. So I'm just writing the first the derivative. Just derivative of this, and yeah, then integral of this thing, which will give me e to the power minus t, and clear? Okay, just integration by parts. Now look at it. If I have 0, if I have infinity here, okay. So e to the power minus infinity by kBt, that is 0. Okay. If I have 0 here, the density of state vanishes at 0. Okay. Which means this part is 0. Okay. What about the second part? This already by definition is the density of states. This is nothing but n e dagger, right? Because derivative with respect to state is basically density of state. Okay. And density of states, what is a partition function basically? Partition function, you know that if I just write it as the probability is always something like e to the power minus h by kBt, and then we have now this is if I do not sum over the states. If I sum over the states, if I sum over the level, so then I write the number of things also. But this is nothing but this thing, right? Which is the Q thing. Okay. Clear. That's why that N into Q we wrote it as that's why we wrote it as a HQ combination. Okay. This is the definition of the probability. Okay. Now think about it. Like then, according to the definition, what is any e to the power minus kBt and the integration of that? That is nothing but your partition function itself. Because the partition function itself is any e to the power minus e kBt, but what partition function it is for the transition state. So this is basically Q delta. But then I have a negative sign because it was a U integral of V dx minus. That minus and that minus now cancels. So what I have is kBt by h. If I write that thing first, Q dagger by Q, okay, e to the power minus E0 by k. Okay. So that is basically the Marcus theory. So basically Marcus showed that I have the same ion equation kind of expression which I derived from the biomolecular reaction rate in a very, very different way. Clear? And but again, we actually skipped many steps in showing it because we showed that there is all these harmonic oscillator calculations we did not show explicitly. But what you can show here is that this probability, if you remember, okay, any probability, the classical probability is nothing but it's a Boltzmann factor divided by the total integration, which is a partition function. if you are doing by level, then levels can be degenerate. So a level of energy E can have n state. That is basically the meaning of density of states. Okay, and then this is nothing but we could have written it like this. So Q by definition is density of states times the Boltzmann factor, and then if we just integrate over all the energies, okay. And here we see the derivative is nothing but the density of state. This multiplied by the Boltzmann factor, and this has to be the partition function. But what partition function? Because this was all in the dagger thing, which is above the E0. Okay. And then basically Marcus showed the canonical rate, okay, reaction rate is equivalent to the bimolecular transition state theory rate. Okay. So, but there is a clear difference. There I had QA, QB. Has to be, because actually there was A and B giving me product. Here actually it's starting from A star itself. Okay. And then he showed that basically, okay, transition state theory is also true for unimolecular reaction. So Marcus basically gave the transition state theory version, which is basically the Wigner's way, the dynamical way version of unimolecular reaction. Okay. And he said that it is basically the same expression, okay, but in a very different way. Because originally, if you remember the way we were writing it, okay, it's very different, like S uncoupled oscillator and that way, right? But at the end of the day, you get the same expression. Alright, so we'll just stop here.